Okay, 8.33 wants us to give some more details about the LDR, about the light dependent reaction. So we are looking at one thylakoid here. So in this image, I just want you to remember we talked about the granum is a stack of thylakoids. So one of these is this, okay? So what we have here when we're explaining this is a couple things that we need to talk about. So we need to talk about photoactivation of our two photosystems. So PS stands for photo, Mr. Fleming, just erase that. So PS equals photosystem 1. Well, PS1 equals photosystem 1. That's over here. Why are they out of order? Don't know. Probably how they identified them. And PS2 equals photosystem 2. These two membrane proteins are where you find the pigments that are going to catch the light. And this is called, I hope you remember, chlorophyll. So that's where you're going to find your chlorophyll. We need to talk about the protein pumps. We need to talk about building up this hydrogen concentration. We need to talk about the reduction of NADP to NADPH plus H, right? Because reduction is gain. And we're eventually going to talk about this cyclic and non-cyclic production of ATP. We're going to talk about photophosphorylation, photo, light, phosphorylation, adding phosphates, right? Where is that happening? Where are we adding phosphates in this picture? Of course, that's how we make our ATP. And do you remember what we call that diffusion of chemicals across the gradient from high to low? Ta-da! Remember in cell respiration, it's the same as this, chemiosmosis. So we're going to talk about chemiosmosis generating that ATP. Okay, so let's talk about the first couple parts here. So I'm going to begin with photosystem 2. That's how they do it. Although the light doesn't go, okay, I'm going to visit photosystem 2 first. I mean, it basically happens at the same time, but let's do it this way. So photosystem 2 gets excited by photons of light. Photons of light are like these weird things that, is it matter? Is it a wave? Like, what are they? So it's kind of like lives in the mystery world. So anyway, this photon of light is the energy, and that photon is actually converted to an electron. So if you see here, we have our electron here, and that is going to activate this proton pump to move protons inside the thylakoid space. So we're going to be generating a high concentration of hydrogen inside here. Also, where do these protons come from? Right here, right? So when light energy breaks water, you remember as photolysis, we're going to have our protons generated on the outside of the thylakoid that can be pumped in. The electron, this electron transport chain, bounces to the next photosystem, here in photosystem 1, and that will cause the electron to bounce to the next protein, the membrane protein. You need to actually remember this name, ferredoxin. And ferredoxin's role is to take NADP and convert it to NADPH plus H. And this is going to be used in the light-independent reaction. Well, we haven't talked about chemiosmosis and photophosphorylation, so let's do that now. So now we have a high concentration of hydrogen protons inside the thylakoid space. They're going to move through this membrane protein, ATP synthase. I'm not sure why they have an E there. ATP synthase, and that is going to add an inorganic phosphate to ADP to create ATP. So ATP will also be used in the light-independent reaction. And remember, the movement of these protons through the ATP synthase is called chemiosmosis.